Edward is a PhD student at the University of Washington, and he works both with Zach, who just asked the question, and also Steve Tanimoto on live programming environments. So Edward, you want to go ahead?
Just a moment. You got that. Great. Let me just go ahead and share my screen here.
Excellent.
Here. Great. So I'm Edward, and I'm here to present Odyssey, an interactive workbench for expert-driven floating point expression rewriting. So there are many excellent tools for floating point error analysis out there, and we all imagine experts working together with these tools to overcome issues in systems that use floating point. However, the reality is that sometimes tools are designed without consideration for the full scope of a user's needs, and then it can feel like the user has to fight against the tool or work unassisted when it comes to following their own workflow. Herbie is a tool that automatically rewrites floating point expressions and usually achieves very low error, as in the example here. This is great because it is fully automated and we can get an answer in about 20 seconds. However, Herbie's result here is incomplete. It's very good for most of the range, but still bad in one place. Human experts can also rewrite expressions. And it's frequently the case that they can outperform Herbie, finding less complicated expressions with no error. However, since this is not automated, it's slow, and there are only so many experts, and there are a lot of people writing floating point expressions out there. So we wonder, is there a way to get the best from both worlds? So let's look at what the user sees when they're using Herbie. They put in an expression, and then they get out a better expression. This is great in some cases. But if the output isn't quite good enough, there's nothing the user can do to advance using Herbie. So are we stuck? And the answer is no, because Herbie is not actually a one-shot tool. The truth is, under the hood, Herbie is essentially doing a graph search, where the nodes are expressions and edges are rewritings allowed by rewriting rules. From Herbie's perspective, there are many possible options. So it would be great if, by being a little bit less automated, we could give the user the same view of the problem. But how would that work exactly? Like, what is a good model for the way that this expert-driven exploration can occur? And this is the question that we want to address. So thinking about this leads us to the notion of a workbench. A workbench helps its operator to work on artifacts using a variety of tools. The tools may be automated or manual, but they serve clear roles. They visualize or alter what you are working on. And a big point of this is that the thing you're working on is external from the tools so that they can all take turns working together on it. So we started to imagine the system, Odyssey, as a workbench that would take over responsibility for managing the user's search and allow the user to leverage many kinds of floating point tools to navigate the space of expressions. And here we have a demo of the system we ultimately built to prototype this. And I apologize because I'm going to have to, oh, actually, I think I can share my sound as well. There we are.
We begin by entering
Hopefully
the
y'all can hear that.
we want to write.
Great.
We can see feedback to make sure it is the right expression. We will optimize over the entire positive floating point range. After submitting, the interface updates. On the left, we see a table of rewritings. On the right, we see an error plot. We would like to diagnose which operations in the expression are causing error. There are two areas with high error. Clicking selects both the rewriting and a particular point. If we then scroll down, we can see the local error analysis for that point. For large values, the square root operation has a problem. Now we select a small value, and for small values, the log operation has a problem. Now let's generate some solutions. Let's start by trying to fix large values. As a human, we happen to know about hypot or hypotenuse, which is a special numerical function for accurately calculating the square root of two squares without overflow. We can already see that this is probably going to have better error. As expected, we have fixed large values. Now, for small values, let's try generating solutions with an automated tool, Herbie. There's An unavoidable pause here while Herbie processes a full rewriting request. In our paper, we describe how we exposed Herbie's internal functions as tools to avoid this delay for the other analysis operations. We now have our results. They are placed in the same table and act the same way as the other expressions that we wrote. They are sorted by average error. By clicking a result and scrolling down, we can see the full text of the result. If we scroll further down, we can see exactly how Herbie rewrote the program. For example, this is a Taylor expansion. Scrolling back up, we can see that Herbie had an idea about using log1p. A good expert would start thinking about rewriting using log1p at this point. However, for demonstration, we will instead focus our analysis on tuning an expression in this region which has some error. To do so, we update the input range. This resamples all inputs and reanalyzes all expressions on the new range. We are going to try to write an expression by hand which has less average error than the best one Herbie has given us. We first deselect some expressions to clean up what is displayed on the graph. We are planning to combine two different expressions using a conditional. First, we copy a branch from the left expression. Next, we mouse over the graph to find a decent branch point. Finally, we combine the left expression with the old hypot expression we want on the right. This gives us an expression with lower error than Herbie's best result. We can confirm that the mixed expression acts the way we are expecting by checking the graph. By exposing internal
Great. So in the remaining time, I'm going to talk about what we can all take away from this. I'll talk a little bit about what we learned from a user study that we performed in order to design Odyssey. I'll tell you how you can work with us if this sounds interesting, and I'll describe what we imagine future work looks like. In the demo you saw, something I want to draw your attention to is that it refers to a particular rewriting workflow, which is described here. Users diagnose errors, generate solutions, and then tune the ideas they come up with to their satisfaction. In our user study, this is the process we observed users using to solve rewriting problems, and we found it useful when designing Odyssey to refer to different steps in this workflow. The workflow gives tools clear roles and relationships. For example, the local error tree and the error plot play an important role in diagnosing error, and they work together. A broad lesson here is that applying HCI methods let us find out that there were sometimes big gaps between our hopes for what users would be able to do and what they were actually able to do with the tool, even when they were excited about using the tool. By acknowledging those gaps, we were able to build new tools to overcome them. For example, originally, users were having trouble figuring out where the error in an expression was, and we added the local error tree to solve that issue. So if you're interested, we are releasing version 1 at the end of this month. There's a link to the VS Code Marketplace here where you'll be able to find the application. As far as how we envision someone might be able to take advantage of this, Odyssey's architecture basically involves remote procedure calls to tools. As an example, in the newly released Herbie 2.0, we made some simple refactorings to Herbie that provide a useful HTTP API for Odyssey. In our paper, we say we turned Herbie inside out because we took useful internal functions like sampling and local error, calculation, and finding a set of many alternatives for an expression, and we made them externally available. So now any other tool that wants to can use that API or easily consume our data from it through Odyssey if it's embedded there. We're actually very interested in studying how we can make it as easy as possible to add more tools to Odyssey. So now we want to bring more users and tools on board to support more use cases. Incorporating output visualization, for example, is very important for this. And we had a couple of participants bring this up in interviews. People really want to know if they have an expression, does the error matter for their application? They want to pick a high error point and see whether that point corresponds to a reasonable input and whether the error is noticeable in real outputs. And this is just one example. Most of the participants we interviewed had ideas about other visualizations or tools they'd like to see added. In the classroom, we see low-hanging fruit around visualizing how floating point calculations work. So there's a ton of research on how interacting with visuals helps students build a mental model of the domain. And these tools that benefit novices also take cognitive burden off of experts by handling the fundamentals for them, as we think we saw with the local error visualization in our study. Finally, there's a lot of discussion about how LLMs will impact various aspects of research, and we wonder if an LLM could be a useful workshop assistant in this case. We already know that LLMs benefit from having access to real calculation tools, since they don't have to pretend to do math if they have a calculator. And we think that Odyssey might be an environment where there are many tools brought together and there's a lot of data to sort through, and having an automated assistant might in some cases be useful. And if you don't trust the assistant, then Odyssey is also an environment where you can check its work against more rigorous tools. So in conclusion, we hope to continue helping experts work together with automated tools. And there's some links here to where you can find the extension to Odyssey and Herbie, and we plan to talk more about Odyssey at WIS 2023. So thank you.
Awesome. Thank you so much, Edward. Great talk. So we have a bunch of questions already in the Slack, but perhaps
we need audio.
Oh.
So I'll stop this.
Can you hear me now?
Yes. Yeah.
Okay. Maybe we should start with a question from Samir. Hello, Samir.
Oh, I thought it was already there. I'm curious about multivariables, multivariable expressions. So does Herbie/Odyssey work with 2 or more variables?
Yes, yeah. The way that we currently handle that is we'll show multiple graphs, essentially, one for each input. And so you can based on the input, you get a different layout of the error. And so you can see for like X or for Y or whatever, how the range of inputs goes. I think for many inputs, the number of sample points, I guess you have to think about how you set your ranges so that you get useful information for a particular input, but it definitely does handle multiple inputs. So
then you as a user must have some insight into where the troublesome area is so that you set the ranges correctly. So there is a risk that you run, which is if you're working with an expression that you don't have some intuitive sense of, that you may not have an idea of how to set which slice of the input space you should be looking at.
Yeah, I think that's an important consideration. Is what we try to do is we try to sample the input space uniformly, and hope that kind of hits some of you see some like spikes in places where there are error issues. And then that lets you kind of zoom down into those areas.
You can kind of gradient descent the error graph.
Yeah, exactly.
Thank you.
Okay, I think we have time for another question, and I'll use my privilege as host to ask it. So you mentioned at the end that there's some that you hope to use this in like a classroom setting. Do you have any ideas or sort of preliminary like results on what kind of activities you'd want people to do in a classroom setting with Odyssey?
Yeah, I think just thinking about it, some things that I've thought about are that I think a lot of people know about things like overflow, but even in the course of our study, I was learning about things about other types of functions that have error like log, so I think it'd be useful to introduce students to the different types of error that functions can have, and to have them work through the process of given something like a quadratic formula or some very typical looking expression showing that we can find out where the error there is, and getting them more used to this idea that there's actually error all around them, and that they should be mindful of that when they're working with expressions.
Okay, yeah, great. So there are more questions in the Slack, but we, as always,